Welcome to all of you, and I'm very glad. Thank you all for coming today to the first lecture of this fall's lecture series, God and Computer, Minds, Machines, and Metaphysics. I would like to draw people's attention to the coming series. This is the first of in total 10 different series. 10 different cognitive scientists and computer scientists will talk about their way to address existential questions within and outside of their research. We have printed a little brochure in which you can find the actual program. I heard today that Tech Talk has actually not quite the latest version of that series, so this is the last and ultimate series schedule. I also would like to draw people's attention to something you can also find in that brochure, which is a discussion group, a non-credit discussion group Harvey Cox and me will held at Harvard Divinity School 4 times this fall to give people the opportunity to discuss questions which come up here in the series in different talks and where they don't have the opportunity to address them within the talk, within the forum on Wednesday evenings. And it is now my pleasure to introduce our speaker for today. Professor Paul Penfield is currently head of the Department of Electrical Engineering and Computer Science here at MIT, which is by far the biggest department here at MIT. And Paul has held this position since 1989. But at MIT itself, he has been far longer than that. He got his doctorate of science here in 1960 and entered afterwards the faculty. And today he is a member of the National Academy of Engineering and was also president of the National Electrical Engineering Departments Association. In addition to numerous other awards, he received the Darlington Award and the Centennial Medal of the Institute of Electrical and Electronic Engineering. Paul has widely published technical issues, but also increasingly about questions on pedagogy and problems in computer science and electrical engineering education. In his time as head, the Electrical Engineering and Computer Science Department introduced a special bachelor program in which students after 5 years receive a Master of Engineering degree. Paul has impressed me since I came here with his humor and also with his genuine interest for students. It is apparent that he cares greatly about graduating students who are unsurpassed engineers and computer scientists, and yet who have also a strong sense of responsibility as individuals and in their role in society. And it's therefore my great pleasure to have you tonight here and you share your thoughts with us on God the Scientist. Paul.
Well, thank you, Ann. I was wondering, actually, I don't know that we need the house lights down all that much. Thank you. Why? Let there be light. Isn't that a biblical response? I didn't know whether Ann was talking about me or someone else. But I am honored to be able to be invited, thank you, Ann, to give this first lecture in the series on God and computers. And it is being held in conjunction with an MIT EECS course, which Ann is offering to students this fall. What I hope to do is to say a few things about the effectiveness with which God is invoked as a way of explaining things. That's my title, God the Scientist. But I have to start with a disclaimer. I'm not educated in philosophy or religion, as I hope you could tell from Ann's introduction. I really know nothing about God. Somebody thinks that's funny? I have no particular religious training, and I regard myself more as a scientist or an engineer than I do as a devout person. Nevertheless, I am active in a mainline Protestant Christian church in the town where I live, and I come from a family in which my grandfather and uncle were both Presbyterian ministers, and one of my cousins today is a UCC minister. Their love of God and things religious, though, never did rub off on me as much as it did on other members of my family. But one thing that did rub off on me was my family's love of good times and of singing. Picture me, if you can, at the age of 10, with my family sitting around the campfire after dinner. Somebody breaks out a guitar, and we all sing along. One old favorite that was sure to be sung with much amateur harmonizing is called Tell Me Why. This is a song that many of you perhaps have sung. It's got a bunch of good questions. Why do the stars shine? Why is the sky blue? One answer to these questions is contained in the second verse to the song.
Because God made the stars to shine.
See, I got God in here somewhere.
Because God made the Irish white. Because God made the sky so blue. Because God made you. That's why I love you.
This is what might be considered the romantic answer to those questions. It appealed to my teenage sisters at the time. Perhaps it still does to their grandchildren. I'm not sure. However, we small boys in the family sometimes came back with an alternate verse, which might be considered the smart aleck answer to these same questions. Whatever you may think of the way that this verse destroys the peaceful campfire mood, at least it does offer answers to these questions, and answers that are sort of based in science rather than on God. Why do the stars shine? Is it because of nuclear fusion, as astrophysicists and little boys would tell you? Or is it because God made them to shine? Or might both explanations be valid and perhaps useful in different circumstances? This is a caricature of the kind of question that I want to try to address today. It's a small example, perhaps a trivial one, of our tendency to invoke God to explain what we humans may not understand. We're appealing, therefore, to God the scientist, and this is how I got the title for this talk. So the question is God a good scientist? How would the answer, because God made the ivy twine, how would that stack up as a scientific explanation? Well, let me explain that in science, explanations are provided by theories. I'll have to say a few things about how scientists go about distinguishing good theories from bad theories, partly because many non-scientists, and I gather there are some non-scientists in the audience here, may not appreciate what a scientific theory really is. For example, some people, if you know a scientist, you might ask him or her, do you believe Einstein's theory of relativity? Do you believe Einstein's theory of relativity? Or another question, are Newton's laws true? Are Newton's laws true? The word true and believe are what I'm getting at. To a scientist, these questions are really not appropriate. They're not appropriate kinds of questions. And I'd like to explain that as a way of going on. To a scientist, a scientific theory is really nothing more than a working hypothesis, one that's consistent with the available evidence. A scientist may use a theory, compare its predictions with observations, but the concept of believing a theory, the way a religious person may believe in God, is not necessary. And if it's not necessary, it's not done in science. A scientist or engineer might have an opinion about how useful or how accurate a theory is, but a theory, after all, is just a tool. If it works in your circumstances, fine. If not, get a better tool. A hammer is a tool. You don't believe in a hammer. You use it when you think it does the job. Now, another common misconception is that a scientific theory is either true or false. Remember the questions, are Newton's laws true? Or are they valid? The misconception is that a scientific theory is either true or false, and that a single experiment can invalidate that theory. However, a scientist would not go along with that. A scientist would only say whether a theory is accurate enough for the purposes at hand. It's not a matter of being right or wrong. For example, Newton's laws of motion, as usually formulated, fail when the motion is at very high speed because of effects of special relativity. This does not mean that Newton's laws are wrong. What it means is that they're approximate. They have their own domain over which they're very effective and can be used. All theories and laws in science are approximate. The important question to a scientist is not whether the law is valid or not, but whether it's good enough for the purpose at hand. Now, don't get me wrong. I'm not saying that all scientific theories are good, and I'm not saying that some of them are wrong. I'm saying that some are good, but some are bad. Scientists and engineers and others who use science in their work do judge theories and render judgments about how good this theory is. And the scientific community is going to reject bad theories by simply not using them. And there's another point that has to be made for the benefit of the non-scientists in the audience. You may not appreciate that there can be, and usually is, more than one theory for a scientist or engineer to choose from. There's sort of a free enterprise competition among theories. Those that are used are those that are deemed most useful. For example, in mechanics, a scientist would have at least 3 different theories which could be used to predict the motion of electrons or other objects. There's Newton's second law, which is usually used in cases where speed is not approaching the speed of light. It's very accurate in everyday use, and it's very simple. Einstein's special theory of relativity is useful when the coordinate systems are in what's called an inertial frame, and Einstein's general theory of relativity is useful when there are accelerated frames and gravity present. Each of these is successively more complex and yet successively covers a wider domain. So somebody who wants to do something in mechanics would have at least these 3 theories to work with. Now think for a moment about the campfire song that we just heard. There seem to be 2 proposed theories about why the sky is blue. One of them, Rayleigh diffraction. The other, because God made it blue. This is not unlike the case of mechanics. A scientist is faced with the need to explain the color of the sky, can choose from those 2 theories, just as another scientist calculating the motion of an electron might choose from among these 3 theories. So how does a scientist tell a good theory from a bad one? And I'm going to tell you what I believe are the 3 most important metrics by which scientists judge theories to see whether they're any good or not. A good scientific theory is one that is accurate, simple, and suggestive. And I'll explain what I mean by each of these attributes. Accurate. A good theory should allow any scientist to predict the results of experiments not yet performed, or observations not yet made, with a reasonable degree of accuracy over a reasonable range of conditions, reasonable domain. The larger its range of validity and the more accurate the predictions, the better. For example, since Einstein's theory of general relativity can describe systems undergoing acceleration, it is more accurate than the special theory of relativity. Okay? One aspect of accuracy that we have to point out is the ability of a good theory to work from first principles without the need of ad hoc assumptions or the need to estimate missing parameters. This feature of completeness, while it's desirable, is really not all that common. Many scientific theories involve parameters such as a gravitational constant, which have to be measured experimentally, cannot be predicted from first principles. But a theory which does not involve such missing parameters is going to be deemed better by scientists. Simple. Obviously, a good theory should be based on concepts which are itself simpler than the phenomenon that you're talking about. It should be easy to use, easy to teach, easy to explain to others. It should not require extensive computation. By this measure, the theory of general relativity, this bottom one, gets low marks. Theory of general relativity gets low marks because it uses curvilinear coordinate systems, which are very difficult to work with. Suggestive. This is something that scientists don't always think about, but a good theory should lead a perceptive scientist to think of interesting new experiments or extensions to the theory, connections to other theories, explanations of other phenomena not originally considered. For example, the general theory of relativity, despite its complexity, the general theory of relativity predicted the existence of gravitational waves. And now scientists are busy trying to find them. They haven't found them yet. And the special theory of relativity suggested the equivalence of mass and energy through one of the branches from it. And that, of course, was discovered and forms the foundation for atomic energy. So these are the three attributes that a good scientific theory has. It's accurate, it's simple, and it's suggestive. So with this as a background, let's go back to the campfire song and ask how God the scientist is doing. The theory, because God made the sky so blue, this is a scientific theory. It purports to explain why sky is blue. Because God made the sky so blue. Now that gets low marks on accuracy. Think about it. Sometimes the sky is blue, but sometimes it's not. This theory does not account for clouds. It does not account for observations made in outer space. On the other hand, Rayleigh diffraction, which I should explain, Rayleigh diffraction is the tendency of blue light to bend as it comes through the atmosphere more than red light does. All light bends somewhat coming through the atmosphere, but blue light bends more, and that tendency is what Rayleigh diffraction predicts. That provides a more accurate explanation. For example, it doesn't fall into the trap of predicting that the sky is going to be blue at night. And the explanation, because God made the sky so blue, you go out at nighttime, what do you expect? You expect a blue sky? Well, so God the scientist is not doing too well on accuracy. Now what about simplicity? It's true that the statement, because God made the sky so blue, is itself very simple. There's no question about that. But the theory is not itself based on simple concepts. Let me point out, it seems that in doing so, God had to make certain choices. For example, why didn't God make the sky green? Well, Rayleigh diffraction would answer that question, but because God made the sky so blue makes you wondering, why not green? Either the color of the sky is an arbitrary choice made by God, or it's related to some property of God, which hasn't been explained yet, or it's an unpredicted parameter of the theory, a missing parameter. Anyway, God the scientist is in trouble with this explanation. If God has some property that sets the sky color, it must be one of thousands of such properties. And what are we to make of any concept which has thousands of seemingly ad hoc or arbitrary choices connected with it? Any model of God with so many ad hoc properties must be extremely complex. Alternatively, if the sky color is an unpredicted parameter, then the theory really fails to explain anything. Because if you ask what color is the sky and say it's unpredicted, you have to measure it. It doesn't do very well. So there's a problem there. Now how about suggestiveness? Rayleigh diffraction really is a good explanation of why the sky is blue. It not only explains why the sky is blue, but think about it, it explains why a sunset is red for the very same reason. Because as the light comes in, the blue sky gets bent more, and the red sky goes and continues to the place where people are observing sunrises and sunsets. On the other hand, invoking God in this context is not really explaining anything at all. We have to come down and say that. It's just a way of closing off discussion or of saying that the explanation is really so arcane that it's not worthwhile to pursue it. And this, I submit, is the opposite of opening up new questions. So it seems that God the scientist isn't doing too well in explaining why the sky is blue. Of course, in God's defense, it has to be said that the campfire song really has nothing to do about science. The romantic mood is, in fact, enhanced rather well by using God to avoid any scientific explanations. And besides, aren't we stretching the point too far? Surely nobody would ever try to use God to explain why the stars do shine. Or would they? The campfire song asks relatively simple, perhaps trivial questions. But there are other deeper questions that science has not yet solved, and God is often called upon to explain those. Let me mention three of these. First one is the creation. How did the world start? Second one, what is life? And what is cognition? Cognition is very germane to the topic of this whole series because, in a sense, understanding cognition is the holy grail of artificial intelligence. So let me mention these three. Although physicists have some pretty good theories about the Big Bang, there's still only speculation about what might have been there before. On the other hand, there are many religious myths about the creation. In my own Judeo-Christian tradition, we learn in Genesis that God created the world in 6 days. It was explained to me when I was in high school that that was because God was a good Jew, and Jews observed 6 days and then had the Sabbath. And the theory was that God was created in man's image rather than the other way around. Well, I don't want to necessarily take sides on that. Christian fundamentalists, on the other hand, accept literally, as a matter of faith, this biblical explanation. Many of them will even tell you when it happened, sometime within the past 10,000 years, 5,000 some number of years. And they might also quote Genesis 1:16. Notice the last line. What were we saying about nobody seriously using God to explain why the stars do shine? In fact, Christian fundamentalists would say that that's exactly what they do. Now let me go on. Life is the second of those deeper questions. Biologists are now beginning to understand the physical and chemical processes that go on in biological systems. Gradually, the theory of evolution is being fleshed out with more details. Experimental evidence is accumulating. One of the most interesting of these happened last May. There was a report of some very rapid adaptation of a species of lizard on a Caribbean island. It seems that within 15 years, after introduction to an island that had smaller branches for these lizards to perch on. Within 15 years, the lizards that were growing up in those islands, this is just only a few generations, those lizards were found to have slightly shorter legs. This effect had been predicted before the experiment was done. These lizards were actually transported to the new island, a series of 11 or 12 islands actually, and a prediction was made, and the correlation between the size of the branches available for the lizards to perch on and the length of the legs was quite striking. And this was in only 15 years. The effect had been predicted. It's not clear whether that adaptation was genetic or not, and this is one of the open questions about that particular experiment. Now, fundamentalists will scoff at the theory of evolution, saying that it's only a theory. In fact, I've personally heard that very statement, it's only a theory. Well, of course it is. Yes, most scientists would agree it is a theory, but then they would point out that it's a better theory than creationism when judged in terms of its accuracy, simplicity, and suggestiveness. And these are the criteria that scientists cherish. Now let me go to the third of those deep questions, cognition. This question seems to be a very difficult one for science. The object of the study can be phrased in many different ways. One of them is to imitate nature by building a machine that seems human. Another way of doing it is to understand how and why the mind differs from the brain. Another way of explaining it is to say that science would like to understand what the soul is. So far, the best efforts of biologists, neurophysiologists, computer scientists, philosophers, and others have not really led to any success. Computers, for sure, have been able to beat humans at some games, such as tic-tac-toe, or even chess, for that matter. But to my knowledge, the Turing test has never been met. For those of you who don't know what the Turing test is, this is a test of machine intelligence. It was defined by the late Alan Turing, who was one of the legendary computer science pioneers. In this test, a person sits and asks questions and tries to tell whether the answers that come back come from another person or come from a computer. A computer that is good enough to be able to trick people into thinking it's human will pass the test. And so far, that has never happened. Maybe it will someday, but it hasn't yet. So cognition is a case where science really has made what I would say is very little progress on the heart of the problem. So here we have some examples where science has something to offer and examples where science does not. And among the questions for which the tools of science don't seem to work, and remember that's the important thing, do they work or not? Not are they true, but do they work? Among the questions for which the tools of science don't work, I think it is useful to identify three different categories. The first category is, doesn't work now, but it's only a matter of time, and everybody believes that sooner or later, science will crack that problem. There are plenty of examples like that. The second category I would have is a category of scientific theory in which science will never work, and it can be proven that it will never work for demonstrable reasons. And the third category, of course, are those in between, where reasonable people can differ from each other as to whether or not science will ever work. And I'll have examples of the last two. First, how about an example in which science will never work? And my friends in the audience who are concerned with computer complexity will jump for joy at this one. Consider a gas such as air. There's already a fairly good theory about the behavior of a gas at a scale of a few millimeters up. This is the so-called macroscopic scale. Concepts such as pressure, velocity, temperature, density, and so on are used in those theories. We know how to design airplane wings, and we know that we can predict with good accuracy how gases flow around various kinds of obstacles. the macroscopic theory works. To be sure, it has a bunch of missing parameters, but once those are measured, it's a reasonably good theory. But there's also a microscopic picture. And think of little gas molecules bouncing against each other. They're little particles bouncing around, hitting each other. One theory which would be useful, and which will never happen, is to predict through simulation of the microscopic molecules what the macroscopic motion is, and thereby to deduce the properties of gases. Now think of it. You have a little container that has maybe a lot of gas molecules in it. If you know each gas molecule's position, you know each gas molecule's direction, the velocity, the property of each one, you ought to be able to calculate what the configuration is any time in the future. And therefore, you could predict the results of experiments that were conceived of at the macroscopic scale. There's a finite number of molecules, and so why don't we just go ahead and calculate it? Simulation, which is what this is a very effective scientific and engineering tool used all the time, and it would be extremely useful if it would work in this case. Let me explain several reasons why it won't. First, think of the number of molecules in question. This number is approximately what's known as Avogadro's number, which you may remember from your high school chemistry. That's the number of molecules in a mole of any chemical substance. And it's really a pretty big number. It's about 6 times 10 raised to the 23rd power. This is really an enormous number, much larger than any number which is encountered in everyday life. And I tried to think of a way in which the size of that number could be explained to the audience. And try this. Consider the best laser printer which you can buy for your personal computer. Laser printer puts little dots on a sheet, and if the dots are small enough, it looks like continuous writing. And these are very successful products. And the best laser printers you can buy have a resolution of about 600 dots per inch. That is, in any inch, you get 600, and in a square inch, you get 600 times 600 such dots. On a single piece of paper, there could be 30 million separate dots. Now, 30 million is a pretty large number, but it's a lot less than Avogadro's number. Now think of the whole surface of the Earth, all the land and all the oceans, all covered with dots of this size. And the number of dots that you'd get, just 600 dots per inch, would be about Avogadro's number, covering the whole surface of the Earth. And that's such a large number that it's impossible to really conceive of in everyday terms. Now consider the practical problem of calculating with this many particles. Suppose each air molecule is characterized by its position, its velocity, its orientation, and its angular velocity. Then any computer that simply looks at the data for all the molecules without even doing any calculations, but just looks at the data, it would take a long time to do that. In fact, if you did that on a very fast modern computer at the rate of 50 million of these per second, it would take about 5 billion years. Now, for those of you who don't recognize large numbers, 5 billion years is the age of the Earth. So if you wanted just to read all the data about this system, it would take the estimated age of the Earth just to do that without even doing any calculations. The conclusion from all this is that a detailed microscopic simulation is impractical because of a large number of molecules that are involved. Remember the criterion that a good scientific theory has to be simple and easy to apply. This one really fails big time. The most that can be done from a microscopic simulation is to predict the general nature of a few macroscopic variables, and such simulation doesn't even do that very well. We cannot predict any detailed motion. Now, it's interesting to note that there are other reasons why this approach will never work either. One of them is the huge size of the computer memory needed to store the data. Another is the impossibility of measuring simultaneously the position and velocity of small particles, which comes from the so-called Heisenberg uncertainty principle. But we ought to be able to get around that by using quantum mechanics instead of Newton's laws. And another one has to do with the extreme sensitivity of the calculations to very small changes in the assumed initial conditions, the initial velocities and positions. This is what's known as a chaotic system. The term chaotic maybe gives the wrong connotation, but systems in science where there's an extraordinarily what's called exponential dependence on the initial conditions is known as chaotic, and this is one of them. This means that it's almost impossible for practical reasons to do microscopic simulation. So what does this example imply about science? What it says is that different areas of science may be separated by a gap that cannot be breached even using the fastest computers imaginable. Different approaches, different variables, different styles, different theories are needed. You know, fluid dynamics, the macroscopic, is really different from any molecular theory that you could imagine. It uses a different approach, different styles. In a similar but less extreme way, chemistry is different from physics, even though chemical systems surely obey all the basic laws of physics. And biology is different from chemistry and different from biology, even though biological systems have to obey all the laws of chemistry and physics along the way. And I will argue in a minute, the mind is different from the brain in a similar way. So let me come to the third open question, which is cognition. And I'm going to assert that cognition, I just gave an example of this category. I'm going to assert that cognition, there's a difference of opinion as to whether cognition will ever be cracked by science or not. One way of understanding the thinking process might be to perform simulation based on a model of the brain. Now, a model of the brain doesn't have to use 10 to the 23rd elements. What does it need to do? Well, the brain has about 1 trillion neurons. That's 10 to the 12th, the last time I checked. Each of them is connected to 1,000 other neurons on average. So simulation using a neural model requires consideration of 1 trillion neurons and 1 trillion times 1,000 other connections. And this is getting to be a pretty large number, even for modern computers. Simulation using the neural model is not going to work because of a large number of neurons, the complexity of the models for each neuron, the number of connections among the neurons, the sensitivity of the calculated results to the details of the initial conditions, and, of course, the speed of even the fastest computers that are likely to be available. The most we can hope for from neural simulation is the identification of a few averages, like in fluid flow, like the pressure and density. To explain cognition, though, it'll be necessary to deal with many more cognitive quantities than you deal with in fluid mechanics. For example, you'd have to predict at least as many results as a typical person would have thoughts or feelings. And how many thoughts or feelings does an individual have? You'd have to make at least that many predictions from any simulated theory. So I assert that neural simulation will not work. What about other approaches? Well, the mission of computer science, at the end of the day, when all is said and done, is to manage complexity. All the things that computer scientists do in one way or another are limited by complexity of the artifacts that they deal with. If cognition is also complex, perhaps the tools of computer science can help. Now, I may be wrong, but I tend to be pessimistic about this approach. So far, there is really very little evidence that the architecture of a brain is similar in any deep way to the architecture of a computer. Without some degree of fundamental similarity, I assert there's no reason to suppose that the underlying concepts would be the same and that the tools of computer science would work. In my opinion, a more likely outcome of study of this, and a very useful one, would be to create new computer architectures that mimic the brain. That's much more likely and would be very useful. Now, there is a field that's received a lot of attention recently, so I should say something about it, that goes under the name neural networks. The structure of a neural network is motivated by the assumed structure of the brain with its interconnected neurons. There is, at this point, to my understanding, no general theory of how such systems work from a theoretical point of view, but they have been made to do useful engineering tasks. But as far as I know, there hasn't been any helpful insights from these activities that have been applied back to help formulate a theory of cognition. I would be happy to be informed otherwise, but I'm not aware of any. So we've seen some approaches which don't seem to offer much promise. Are there other approaches that will work? I assert that there's no clear evidence one way or another. This is a debatable case. A lot of people have put a lot of effort into working on this without success. And I'll tell you what my opinion is here, and this will not be the opinion that's shared by everyone in this room, but my opinion is that there will never be a good scientific theory that explains cognition. A theory that, like other good scientific theories, is accurate, simple, and suggestive. Remember, a theory that stands up to judgment and criticism of scientists. Now, I'm not trying to denigrate research in this field. On the contrary, some progress has been and will be made in this area. There will be lots of results obtained along the way, which will be very useful. For example, in guiding the design of man-made systems, such as computers, robots, and so on. But in my opinion, and this is debatable, and therefore other people can have other opinions, the lofty goal of explaining cognition scientifically will not be achieved. Now, if we accept that assertion, or even if we don't accept that assertion for that matter, and if we only say that cognition is not yet understood, the people who believe that it will someday be understood are in this category. If cognition is not currently understood, and I say it never will be understood by science, some things are therefore excluded from the realm of science. And those are things that are naturally related to self-awareness, things that are felt internally, personally. And I'm going to lump these together under the name human nature, although that isn't quite the right concept. I think it's pretty close. These include thoughts, aesthetics, desires, feelings, emotions like love, grief, jealousy, hatred, intellectual capabilities like instinct, judgment, intuition, intelligence. These will not be adequately explained by any scientific theory. So what alternative do we have? If we need to reason about one of these topics, or for that matter about any of a number of other topics that are not now understood by science, if we need to reason about them, it'll have to be done by non-scientific means. One such approach is to make assumptions that are not justified by science and then to proceed. These assumptions are sometimes called leaps of faith, and science in general tries to avoid such assumptions, whereas most religions and many other human activities seem to require them. But of course, faith is an intensely personal matter. What one person assumes will generally differ from what another assumes. And science, by its very nature, produces results that are supposed to be able to be reproduced by others. So the leaps of faith are inherently non-scientific. I want to call this approach faith-based reasoning. Whether or not the concept of God or religious concepts are involved, assumptions that are not justified scientifically, I want to call faith-based reasoning. Faith-based reasoning inevitably lacks the scientific criteria of accuracy, simplicity, and suggestiveness. it's tempting to say that it's therefore bad science. Well, maybe it is, but maybe it's the best we have. And maybe if we keep in mind the underlying assumptions, keep in mind the leaps of faith that are made at the beginning of the analysis, maybe we can still have some reasonably useful theories. Lots of people we all admire: artists, architects, doctors, managers, musicians, social scientists, and engineers, for that matter, rely in part on science and in part on understanding of human nature and social systems. And if, as I assert, human nature cannot be understood by science, and if we get too smug about discounting anything non-scientific, we may be left with no tools at all to work with. Another point: we scientists and engineers should not forget that science as an endeavor is itself based on a set of assumptions. We use mathematics, logic, deductive reasoning, and a host of other tools that, in the final analysis, are not themselves provable by any rational means. We all assume that the behavior of nature is not changing with time. How can we be sure? When you really get down to it, we use all these assumptions underlying science for what is really a very simple pragmatic reason, and that is that they work. Why shouldn't we be prepared to be equally pragmatic in considering whether to use faith-based reasoning? The important question is, does it work? Now, there is another reason we should not look down upon non-scientific reasoning too much. Science itself is a human activity. We scientists are ourselves humans, after all. We have our own personal thoughts, hopes, dreams, feelings, and emotions. And I assert that those cannot be explained by science. From time to time, we all pursue activities that are not based on rational thought, I'm sure. Sometimes when doing science, but at least off the job, enjoying fine music or beautiful art. Even those, there's no scientific explanation of aesthetics. Even on the job, science deals with artifacts and theories that scientists themselves consider to be things of beauty. So aesthetics, even as applied in the judgment of scientific theories themselves. As for another example, let's consider the emotion of grief. Many of us in this room know what it's like to experience grief resulting from the death of a close friend or a relative. Right now, the entire MIT community is going through a period of grief over the tragic loss of a freshman, Scott Kruger, to alcohol poisoning a few days ago. Now, this emotion of grief is a very real one. Someday, science may have something to say about the neural patterns associated with grief. Science may even develop a specific mood-changing drug that inhibits those patterns in some ways. However, I assert that grief also has a deeper emotional side to it. And if you need to cope with this aspect of grief, you might find helpful support in societal mechanisms, including religious ones. Many people have found that a faith based on a belief in God is effective in providing solace and comfort. Not many people would receive much consolation from knowing that their grief is somehow related to chemical imbalances in the brain or patterns of firing of neurons. In other words, in handling grief, science doesn't help, but a belief in God does. Let's be pragmatic. If it works, that's the important question. As for another emotion, love, I sincerely hope that everyone in this room has or will experience the joy that accompanies total, unconstrained love for another human being. It's a wonderful thing. It may be true that sex, the physical side of love, is somehow explained by chemical hormones, as the smart aleck verse of a campfire song says. chemical hormones. That's why I love you. But I assert it's surely true that the deeper emotional and spiritual aspects, and ultimately the more satisfying and pleasurable ones, are better described by a romantic answer, such as, because God made you, that's why I love you. And I'd like to wish for everyone in this room the chance to say to your loved one something like, what to tell your loved one? Chemical hormones, that's why I love you? Or wouldn't you rather say to your loved one something like, because God made you, that's why I love you? Thank you for your attention.
We have 20 minutes time for questions. Thank you, Paul. That was a wonderful talk.
Thank you. Thank you.
We have 20 minutes time for questions. So are there any questions, comments, or?
You mentioned that cognition and human nature will never be understood.
Well, that's my opinion. Other people differ. And I was careful to say that that's in that third category.
Why do you say that? I think that you have an extra mind.
Okay?
Because you're a believer, and you're putting a lid on it. And it's very unscientific.
Well, it's true that that's an opinion, and therefore it's not subject to the same kind of scientific analysis that I would like to apply to calculate the trajectory of electrons. That is true. I'm basing it on the following observations, that a lot of very smart people have worked for a long time and made very little progress. Computer science has this open question called, is P equal to non-P, equal to NP? There are certain problems in computer science that can, in principle, be solved by running a computer in a time which is known as polynomial time. That is not too fast. And there are other ones for which nobody has yet discovered a procedure or an algorithm that works that way. It's never been proven. I think most every computer scientist, if you ask them, is P equal to NP? That is it possible eventually to find a polynomial time solution, would say no. But it's never been proved. And the reason they would say no is that a lot of very smart people have worked a long time and never made any progress at all, really, on that. Now, some of my colleagues are going to differ with me, but I think that most of the computer science you'd approach would express an opinion that P is not equal to NP. Now, I'm expressing an opinion that's based on the same kind of evidence, and I would be happy to listen to other people who can explain why they have a different opinion.
I would like to hear some atheists making those assertions.
Well, I think
that will have more credibility.
If you come back in 3 weeks, Rodney Brooks will talk about artificial humanity. It is exactly on
yes.
October 22nd, and he's atheist, and he will talk about this very same issue.
That's right. Anne has done a marvelous job of getting people with different fundamental beliefs here. And I will have the wind knocked out of my sails completely by Rod Brooks, who knows much more about this subject than I ever will.
I don't know. Do you want to handle a question, or?
Okay, questions?
Isn't the crux of the matter...
Now be sure that you speak loud enough so that everybody in the back can hear.
It seems to me that the crux of the matter is you have to first acknowledge there are different ways of knowing.
I don't know what it means to know. As a scientist, I will take a tool and use it where it's appropriate. As a carpenter, I will use a hammer or a screwdriver, and I know when to use what tool, and I've learned what tools work. What's it mean to know?
Paul, I liked it all the way up to a certain point, and then you took a leap that I think leaves a lot, which is, you've split it into this...
You mean you got through the first 5 minutes?
Right? You did this bifurcation of the choice as to whether we have a scientific theory by which, to you, you mean a scientific theory like physics.
Yeah.
Okay?
Yeah.
Or, on the other side, you have things like faith in God. And there's this huge middle that I think is an enormously rich part of human experience, including all of the social sciences, which have theories, which although not tested in the same way or coming up to the same level of, in some sense, abstract scientific perfection as, say, physics, nevertheless are very useful theories, and yet still are not based on faith faith in, say, God or religious values, and yet which still are very useful. And there's a whole range of...
When are you going to start disagreeing with me?
So what I'm saying is, why is it you pose it as this choice between
No,
these
I
two
don't.
things
No, I don't.
when you've skipped over this whole huge middle thing, which may be an even more adequate explanation for the various things that you've described here?
No, Charles. Remember what I did. I said, when you don't have a good scientific theory, you have to make some assumptions. And I called them a leap of faith. And that doesn't necessarily involve religion, doesn't necessarily involve God, doesn't necessarily involve, but it does mean an assumption. But if you can keep a number of assumptions small, you can have a better structure that's built on it. Maybe the social scientists do that reasonably well. There certainly is a big middle ground, and it isn't as though you have on the one extreme the scientists who don't have any assumptions. In fact, I tried to say that science is itself built upon unprovable assertions. And on the other side, religion. I don't think it's like that at all. I fully agree with you that in the middle there's a complete gradation of problems.
I have a kind of a sneaky praise to the pragmatism of religious thinking. And one, I have a hypothesis that people may have a religious instinct from birth. It's very
A
useful
hypothesis that someone may have a religious
It's very useful
instinct.
for an infant to believe that the environment will respond to it when it cries, for example, and that the environment watches it. It's kind of true, but the environment is the parents. And then it's nice to live with that feeling. But whatever else you have, like love and all those wonderful feelings that you cannot explain, it's nice to you to just believe that they are wonderful and that they fill the whole universe, instead of going and studying cognitive science, and you come up with all those useful metaphors, and you can, by the way, increase those things just taking ecstasy or whatever. But the thing is that when you start believing that there is some unknowable entity whose structure you don't even postulate, who makes those things work in a way you don't care to explain, then you make some leaps that are just sloppy thinking.
Well, you may call it
feel
sloppy
better.
thinking,
You feel
but let me
better.
come back to the point that I was trying to make. In coping with grief as a specific thing, if your wife dies or if your mother dies or something like that, you surely have an emotion. There's no question about that. What do you do about it? I assert that that's an area where sloppy thinking, as you call it, has in fact, over the years and over the centuries, provided help. So be pragmatic. Is it going to help you or not?
So you can see that this belief makes me feel good, and
Yeah,
I don't care
yeah.
if it's subjective. So, but when you start asserting its subjective status, then it's wrong. And that's what people say, that God objectively exists.
Well, I didn't say
Feel
that.
good too.
I didn't say that. Maybe some people do.
I'd like to follow up on his use of the example from grief there. It doesn't seem to me that what you're talking about actually explains anything about grief. It seems
No.
like it's some other aspect of grief. It deals with sort of the human interaction with grief
Yes.
without saying anything about what grief itself actually is. And the scientist, it seems to me, is interested in what grief actually is, not how humans interact with grief.
Well, I think science may someday associate specific neural firing patterns and this sort of thing. May talk something about the biochemistry of a brain when that's undergoing grief. I think there's a lot of opportunity to discover things that are not currently known. What you're saying is that my illustration about how to handle grief is not so much science as it is engineering. And I got to admit, I'm more of an engineer than a scientist. Rather than understand, in some sense, whatever that means, I want to build and provide solutions to problems. And being presented with grief, I maintain, is a problem that if I can find a solution for it, then I've served as a good engineer. And so you're quite right that it isn't so much the, my example doesn't so much point to science as it does to providing solutions for human problems, which is what engineers do.
Talk about engineering versus science. I mean, we built machines that can beat humans at chess. We didn't do it by figuring out how the mind does it and trying to mimic it. We just did it. And so my question is, even if we grant...
Brute force pays sometimes. The first tic-tac-toe machines were brute force also.
Right. We've also done other things that weren't, get farther and farther being brute force and end up being more and more clever. I guess my question is, even if we never have a theory that explains how it is or why it is that people do what they do, why is there any reason to think that we won't be able to engineer a system that can think as well or feel as deeply or be as self-aware or even more so than people are?
Well, this is a theme that I've heard before, and it's an important one. Do we have to imitate the structure of nature in order to get the same function of nature, is a way of phrasing that question. Do we have to actually understand, in some sense, all the relationships in the brain in order to make something that will behave as a brain? And you're asserting that we probably do not, and I would agree with that.
In fact, one would argue that if you want to build a fast computer, you should not be mimicking the brain, because I mean, we have those brains already. You want to do something better. And by mimicking it, you just do no worse, or rather no better than, and mostly worse than the way the brain works.
Yeah, I think I agree with that. That if I had a well worked out solution to something and I wanted to do something better, I'd take a different approach, and maybe that's what we should do. Nevertheless, I assert that there are a lot of domains in which the attributes that a brain has, slow but able to deal with ambiguity and a lot of things like that, would be very useful in engineered objects, and therefore having one which had some of the architecture of a brain might be useful. Yeah, Jerry.
You divided the questions that are possible into three classes. They were formally or at least practically unknowable. There were the things that were clearly understandable by scientific method, and they were the ones that were debatable.
Yeah.
But, and then you took some of the
That's
debatable
yes,
ones.
no, and maybe.
Yeah, and you took some of the debatable ones and said, well, gee, it's practically probably appropriate to consider them possibly unknowable. One of the things I'd like to say is I think a meta point here. I think it's extremely bad to ever move something from the debatable into the unknowable by your belief.
Yeah.
The reason for that is because it inhibits the investigation of such a thing, which might turn out to be knowable. So it's always to our advantage, even in what appear to be almost hopeless situations, unless there are mathematical proofs. It is always to our advantage to apply effort against the things that are currently debatable. That's the end of it.
I think there's a lot of truth in what you say. Nevertheless, my charge from Anne was to give a personal view. And I gave a personal view. I am pessimistic about that particular line of research accomplishing that grand objective. Now, it can accomplish a lot of other things. You're saying that it's counterproductive for people to say that too loudly because you'll destroy the motivation of a lot of people. Even to themselves. Okay. There's some truth to that.
How much promise comes from the quantum theory of quantum mechanics in answering some of the
The question is how much promise comes from quantum mechanics or quantum theory in answering some of the questions. And I don't believe that, that quantum mechanics has any improvements over it. I don't think that it has anything to offer that hasn't already been talked about here. I don't think that that particular theory. There is one example that I cited in the molecular simulation of a gas where there is the theoretical impossibility of measuring accurately enough both position and velocity. And what you have to do is choose new coordinates that don't have that problem. You have to take into account quantum mechanics. And so you can probably get around that, but that still doesn't make the problem solvable.
It seems like there's a mutual exclusivity. They're mutually exclusive. Where you have faith-based and scientifically based theory. And I'm curious, why isn't it that it is just two coordinate systems? Yeah, hi Rocky, you found it.
There's also dog-based theory.
Dog, the scientist here. Is it that there is a superset that is basically faith-based, and as we get better at the complex analyses, as our computers get bigger, then we eat away at the universal set of faith-based? Or is it that there is a faith-based in both the simple and the complex? For example, maybe God made Raleigh's diffusion.
Well, let me try to attack that from the following point of view. Some people that I've talked to about this assert that you start off knowing nothing, and therefore everything has to be because God made them. I mean, there was a time when God was used to invoke how the tides worked and all sorts of things, okay? And then gradually science chips away at that, eats around the edges and grabs portions that can be, you can use scientific method to make predictions that are more accurate, simpler, and so on. So it's better science. And some people have the model that there's this wall that is gradually being encroached upon. Now, that's not my view. My view is closer to the one which Charles Lyserson came up with a few minutes ago, which is there are a large number of endeavors in which some combination of reasonable assumptions that can be justified and assumptions that cannot be justified are mixed together in some way, in a way that's been found practical and useful. And I tend to believe that that's more the case, and that it's a lot more complex than the simple wall between the known and the unknown.
I'd like to test the limits of your pragmatism. It seems to me that when dealing with things like grief, it could be that astrology might work,
Yes.
channeling might work, crystals might work,
Yes.
alcohol might work, all kinds of things might work. Are they all okay?
Well, I would assert that astrology has overtly, one of its objectives is the same as science, to make predictions. You pick up a morning newspaper and you read your horoscope that you will come into a bundle of money in the next week or something like that. So that as an endeavor is attempting to do the same sort of thing that science does. Now, is it as effective? I believe that most people would argue that it's not as effective. It's got a poorer track record of accuracy, and it's got hidden assumptions all over the place. So in that sense, it would be bad science. Now, if your grief is in fact relieved by astrology, I don't know what to say. I doubt that that would be true for very many people. I think it is true for a larger number of people that organized religion does provide ways of handling things like that.
We have to stop here, unfortunately. We could,
Wait a minute. Let me take a couple more.
Okay, good.
Yeah.
Well,
If the audience can stand it, I can stand it.
no, I mean, I'm thinking more about these.
Okay.
So you said, like, there are two ways to explain, like, why the sky is blue, and one was God, the other one was scattering. And my question is, well, my question is that really, if scattering really explains why the sky is blue, because if you say, okay, scattering explains it, but what is scattering? When, how scattering happens? And so my question is exactly that at the end you can always say, wait, God made scattering and make it happen, and that's it. So I think that science, more than really explain, like kind of describe like how things happen, and sometimes explain is better than others, and so it works better than than other. But at the end, is that really an explanation of
Well,
everything?
you brought up two issues. One is just the term relative diffraction doesn't get very far. You have to understand what it is, you have to work through the equations, and you have to understand that light has a spectrum and so on. And there's a lot more to it than just that one term. So that's certainly true. I think you're also asking the question, these are these two so-called explanations of why the sky is blue. You're asking, couldn't they both be true? And the difficulty that I have with that is that they probably can both be true. That's not out of the question. After all, we've got these three laws of mechanics that I put up. And when you're dealing with certain domains, all three of them make accurate predictions, and all three of them are, in that sense, useful theories. Some are easier to use than others. But yes, you can have more than one scientific theory. So, but each one ought to be judged on the basis of its accuracy, simplicity, and suggestiveness. And so, let me just take you're the boss.
You can go ahead for 3 or 4 more minutes.
3 or 4 minutes.
I'm struck that there is some common ground that you have between science and these other faith-based assumption systems.
Why did you assume something about me that wasn't true?
Well, that's pragmatism.
Yeah.
And what I'm wondering is, if you get into areas like grief or love, and you're taking a pragmatic approach there too, just as you are in terms of your science engineering, whether you can specify other criteria besides accuracy, simplicity, and suggestibility that would allow in these human dimensions, that would allow your pragmatism to be a little bit more reasonable. As you could test some of the, let's say, look at world religions. You know, you could test the Christian faith as to how well it alleviates grace versus, let's say, Theravada Buddhism, which is atheistic. So, but I'm wondering whether there couldn't be some versions of pragmatism in these human areas that you could, specify more concretely what the criteria for workability might be.
That's an interesting thought. I don't have anything to contribute to it myself.
I pick up on the question of this woman here.
You better speak louder.
Pick up on her question. I heard her question a little different, so I'll try to rephrase it. Is God the scientific lawmaker? Newton, from my perspective, was involved in spiritual practice, trying to identify the laws of God. And those laws are that he identified, he used scientific method to do it. Einstein used scientific method. You all use scientific method. But is it God the lawmaker behind those laws? And you move into another realm. I know Laplace said you don't need that assumption and you can drop it. But that's the question maybe I think she was trying to ask.
My answer to that is that science doesn't care. And if it's beyond the provable and is outside and cannot be measured, cannot be tested, then science has nothing to say about it.
But the recent science issue of the magazine Science showed that a lot of scientists do care, and that I think is a later session here.
Well, I think it showed that scientists are human beings, and they have the same spectrum of emotions, the same spectrum that other people do.
As a spiritual practice in part. Many scientists secretly are doing it because it's
Well, I would submit that many successful people in many different disciplines have an existential pleasure from doing it, which is of that same nature. I love being an engineer. It's the same thing.
We have to stop here.
We have to stop.
Unfortunately, we have to stop here. Paul, thank you so much for inviting us, please.